Hello and welcome to another walkthrough. Now this time it will be Edexcel A2 level, Pure Math Paper 1, June 2025, which I have never seen before. So this is going to be a blind solve for the entire paper under the real exam conditions. So along the walkthrough, I might be making mistakes, which I'll correct if I realize in the walkthrough. But if I don't, I'll annotate the video. And I'll try to explain the worked solution and the thought process as simply as possible. At the end of the walkthrough, I'll mark the paper anyway. For those of you who make mistakes a lot of time, you might benefit from seeing me making a mistake and correct it later. So this walkthrough is not meant to just show you the destination of the solutions, but also show you the journey to the destination. If you feel like jumping to a particular question, you can use chapters in the description. Otherwise, stick around. You might be getting some tips along the way. If you are ready, I'll see you in there. Okay, so this is the paper. And I'll start the timer now. Okay, let's get going. That's number one there. I'm going to do it here. Number one, the point 6 minus 4 lies on the curve with equation that. Find the point to which P is mapped when the curve with equation that is transformed to the curve with equation that. Alright, so this is actually similar to the first question on the same year in the AS level paper, right? Transformation of the graph. Alright, but they don't show you any graph here. They just give you points. So f x plus 2 would be shifting, right? Would be shifting the graph to the left by 2 units. So point P would be then 4 minus 4. Yeah, you just subtract the x coordinate by 2, right? That's it for A. Part B, y equals f inverse of x, right? So this one is a little more tricky here because you would need to think about how the point, which is 6 minus 4, this is 6 and minus 4 here, maybe, is gonna flip about or in the mirror axis here, which is y equals x. So basically, it's gonna be, if you have 6 minus 4, so it's gonna be flipping the x and the y. It's like swap the x and the y coordinate. So it could be 4 and 6. Yeah, let's try 4 and 6 if it makes sense. So if I have 4 and 6 here, it's going to be somewhere here. So it's probably not going to be 4 and minus 6, right? Minus 4 and 6 is probably too far. It would probably be around here instead. So 4 and 6 is around here. My graph is probably not to scale, but you get the idea there. All right. Okay, let me think again. So if I have minus 4 and 6, it's going to be that. Actually, it could be that. Yeah, hang on. It could be this one because seems like this one is not reasonable. It's a bit off there. My graph is probably not to scale, but I noticed that if I draw a line perpendicular from the axis to the point, I'm going to have this distance right here as well, yeah? And it should be going to the other side like that. So I'm just going to take my chances here to answer minus 4, 6 instead, yeah? And that probably makes sense to you guys, hopefully. So that's going to be minus 4 and 6, yeah? At least you're going to have to swap the 6 and the minus 4 somehow, but the minus might go somewhere or might not have it at all. Like if you have this, it might be, so if you have this, yeah, sometimes they just swap the numbers but not the minus sign. Like for example, if I have, say, somewhere here, I don't know, maybe minus 3 and 1, for example. Let's say the point is here. Minus 3 minus 1, which is the third quadrant, right? And then if you sort of flip this point or mirror image this point in the y equals x line, it's going to still be somewhere in the third quadrant, which is, so that would be minus 1, minus 3 instead, right? It would be around here. Yeah? So you still keep the sign. That's the bottom line there. So the sign might be dependent on the quadrant. But in this case, I came up with 2 cases where you have 4 and 6 or minus 4, 6. I think this one makes more sense to me, right? This one makes more sense. So it should go the other side like that. Yeah. So I'm going to go for that. All right. And C, we have 2 modulus fx minus 3. All right, so we're just going to do the transformation in order here. So you're going to modulus the fx first. That would mean, changing the sign of the y coordinate to a positive. So we have a minus 4 there. Okay, I'm just going to do 6 minus 4 here. So if you do modulus fx, it's going to be 6, 4 first. Yeah, in order there. And when you multiply by 2 like that, it's going to be 6 and 8. You multiply the y there. And then you minus 3. Yeah, after that. So just going to write everything. Then you're going to have 6 and 5. Just shifting down by 3 units. So the answer is 6 and 5 there. Okay? So take the absolute sign of minus 4 becomes 4, 6. Multiplied by 2, 6, 8. And minus it by 3 becomes 6, 5. So that's the answer there. Alright, so I think I'm good with number 1. Number 2. The circle C has equation that A state the coordinates of the center. Well, that's simple, right? So AI state the coordinates of the center. So center C is, you just take the critical value of the brackets, which is minus 3 for the first one and 4 for the second one. And I find the radius of R, writing your answer in a fully simplified surd. Okay, so radius is root 24. Well, because 24 is, we can write it in a square number times something else. So 4 times 6, right? And 4 is, you can take the square root of 4 out of the surd, so it's going to be 2 root 6. Yeah, and that should be the answer there. Okay. Part B, determine, giving a reason whether or not the origin lies inside the circle. Well, for any point to lie inside the circle, you're going to have like an inequality like this. So for anything to lie inside the circle, you're going to have to satisfy this inequality. Yeah, it's like if you think about it in like a shading area perspective. If you have, let's say this is the circle, right? Minus 4, 3, and with the radius there. So if we want to shade the region satisfying this inequality, it's going to be inside the circle, right? So if we want to check if the origin point is in the circle, we just plug in and see if it satisfies the inequality, right? So x equals 0, y equals 0, yeah? So we have 3 squared plus minus 4 squared equals, see if it's less than 24. And that turns out to be 25, right? Which is not, which is greater than 24, yeah? This is area in circle. We have to satisfy that inequality because 25 is not less than 24. So this is not in circle, right? Therefore, origin is outside, or should I say not inside the circle. C, yeah, that's it. Just substituting in and verify it, yeah. Okay. Number 3. The first 3 terms of an arithmetic sequence are that where k is a constant. A, find the value of k. Well, arithmetic means that you have a common difference, right? So a common difference means that if you take the difference between 2 adjacent terms, you're going to get the same value. So 10 minus 6k is equal to d, which is equal to also 2k minus 10. Yeah, like that. So we just solve for k. So I'm just going to do minus 8k equals minus 20. Yeah. So k is going to be, I'm going to simplify that by 4. So it's 5 over 2. Yeah. So k is 5 over 2 there. Part B, hence find the value of the sum of the first 50 terms of this sequence. All right. So sum of the first 50 terms, so S50 equals, I'm going to use that formula, 50 divided by 2 and then 2 times the first term being 6k, so 6 times 5 over 2, that's the first term, plus n, which is 50, yeah, minus 1 times d, which is what is d? So d is 10 minus 6k. Let me find d first. So d is 10 minus 6 times 5 over 2. So that's minus 5, right? Isn't it? 5 over 2, 5. Yep. Okay. So this is going to be minus 5. Substitute it in. Okay. So we just find that. Yeah. Well, okay. So that's 25 times, in brackets, the first 2 times a there is just 30, right? Because that's, you get 15 times 2. And then plus, what is this? Minus, it's just 49 times minus 5. Okay, let's do calculator there. 25 times bracket 30 minus 5 times 49, like that. Yeah. Yeah, I plug everything in correctly. Let me check this side. Yeah, I'm gonna be fine. So minus 5375. Yeah. Okay, so that's the answer there. Not that bad. Number 4. Given that fx is that cubic function and f of minus 4 is 0, write fx in the form of that. Right. So basically, you know that f of minus 4 is 0, that means they're telling you a factor here. So it's x plus 4. Yeah, the opposite sign is a factor from that information. Now you can do comparing coefficients or long division. Yeah, you can do that. I mean, I'll show you how to do short division, because I think that they don't require you to perform like explicit long division here. You can just come up with that, and then with all the coefficients correctly, and you'll get all the 3 marks there. But okay, I'll show you both methods, right? So I'll do long division here, just in case you guys, some of you might not know how to do it properly yet, or like you have forgotten or something. Yeah. So that's a long division. Yeah. So we divide the first into the first, we get 2x to the power of 2 there. Yeah, and then we multiply back, we get 2x to the power of 3 plus 8x to the power of 2. We subtract second from the first line. We get 0 for the first one, of course, we want that, and minus 5x squared here. And then we do it again. First divide into the first, we get minus 5x now. And oh, I forgot to pull this down first, sorry. Got to pull minus 16x down first. And then yeah, multiplying back, I get minus 5x squared plus 20x. No, that's minus 20x. Yeah, and then we subtract them. The minus 5x squared goes away, and then we have minus 16 minus 20 here, so it's 4x. Pulling that down. Now this is obviously 4 for the quotient. Yeah, so this is 4x plus 16, and of course if you subtract that, you get remainder of 0. So that is just to show that because qx is a quadratic factor, so you can write them down like this. And that is a long division there. Yeah. So that's the answer. Now that's called long division. I'm going to show you a short division. Yeah. Let's see. So instead of writing all the terms in their algebraic forms, we're just going to take the coefficients. So the coefficients of the dividend here, the thing to be divided, is 2, 3, minus 16, 16. If there are missing terms, like let's say there wasn't a 3x squared, you got to put in 0, just like you do in long division. And instead of a division sign like that, I'm going to do like this, flip the other way around. Now the divider, yeah, it's not going to be a plus 4 or x plus 4, it's going to be minus 4. So you take the critical value instead of the actual number there. Now the first step, you're going to pull 2 down. So this will correspond to that, right? Similar. Always pulling the first number down. Yeah. And now instead of multiplying back, and subtract, you're going to multiply back and put here and add. So if you multiply 2 back to minus 4, you get minus 8. It's kind of like reversing or doing the opposite operation under the hood, if you like. And I'm going to add, so I get minus 5 here. You see that? You see minus 5 correspond to that now. Yeah, and then I multiply this back, I get 20, right? And I'm going to add between minus 16 and 20, I get 4. You see? That's correspond to that, right? And then, of course, if I multiply this, I get minus 16. That confirms that if I add them up, I get 0. Now, because the dividend starts from the third power of x, so we're going to start the quotient here, which is the result from the division, from the second order. So you write 2x squared minus 5x plus 4, just decreasing order like that. And that is the result of the division. You got it there. So they lead to the same answer, but I think short division is like a trick, like a faster trick there. I might be wrong here, but at least I've seen some mark schemes, they don't require you to show a long division. So they just probably have this in the mark scheme, and they write M2 and A2 or something. Like you show somehow some method. They don't care much about the detailed long division. So maybe you should try learn more about the short division, guys. All right. And that's it for part A. Part B. Hence prove that minus 4 is the only real root, right? So it is basically asking you to show that this wouldn't give you any answer. This quadratic factor doesn't give you any solutions to the function of x. So we prove that by just doing the discriminant, of course, of this quadratic factor. Yeah, so it's going to be b squared minus 4 times a times c. Yeah, so let's see what we get here. So it's 25 minus 32, and that's a negative 7, which is less than 0. So there's no real roots here because the discriminant is less than 0. Therefore, the only root of fx is indeed minus 4. Yeah, that's it. Okay, next question, number 5. Yeah. Express that as an integral, right? So don't be intrigued by this complicated looking notation. It's just basically integration. This is the fundamental theorem of integration. This is by Riemann sum integration here. So basically it's like, you know, you might have seen that kind of animation all over the place in YouTube or elsewhere, that integration is like finding the area under the curve, but you can do that also by finding the sum of the strip area. So if you divide the whole area into strips like this, just like trapezium method, you're going to have to sum them up and you get the integration as well. But technically, that is only accurate, right? When you do trapezium, right? Actually, the area is not exactly under the curve because you have, differences there between each trapezium you have compared to the curve there. But imagine if you sort of like make the strip width infinitely smaller and smaller, the strip will be more and more close to the area under the actual curve. And that is the reason why they have the delta x here, the del x, which is the strip width, being closer and closer to 0. And that is just the definition of integration, basically. Okay, so it's just integral. I've talked too much, maybe. The lower limit is 1.44 here, and upper limit is 2.89. Yeah, and then this is 2 over root x dx. That's it. Yeah, that's 1 mark, no problem. Okay, just checking numbers there. Yeah. Hence show that that is equal to k, where k is an integer to be found. All right, so we're going to integrate that first. We integrate that, well, let's write it in an index form first. So we are basically integrating 2x to the power of minus 1/2, right? Got to be careful there. So this is equal to 2. I'm putting 2 outside. X to the power of minus 1/2, if you add the power by 1 according to the power rule for integration, you're going to get a half. And you have to divide that power half on the term, right? So you get 2x to the power of 1/2, like that. Because 1 divided by half is 2. And then you put in the limits, yeah? So if I put the 2 out as well, I'm going to get 4, yeah? You can just extract that out. And in the brackets, I have putting the upper limit. This is square root 2.89 minus square root 1.44. I happen to know that square root of 289 is 17, so that's going to be 1.7. And square root of 1.44 is 1.2, so that's going to be, yep. So that's 4 times 0.5, which is 2, yeah? An integer to be found. There you go. Okay. Number 6. A scientist is monitoring the flight of seabirds after they leave their nests on a cliff. The height above the sea, h meters, of one of the birds is modeled by the equation, an exponential equation there. H greater than 0, t is in between 0 and capital T, where t seconds is the time after the bird leaves its nest. And A, B, and T are positive constants. Given that the bird was 17.6 meters above the sea exactly 4 seconds after it's leaving the nest, and 11.9, okay, it's giving you 2 conditions, and we want to find the complete equation. This is very much like the AS paper on question 13, I remember, on the same year here. Because that question I flopped a little at first, and then I corrected myself later. You can just try check that one as well if you want to see, yeah. So we're just going to use the 2 pieces of information here to make 2 simultaneous equations, right? Yeah, so it's 17.6. The h value equals a minus b, and then t is this is actually not exponential, it's polynomial, sorry. And 4 to the power of 1.5. And the other one is 11.9 equals a minus b, 9 to the power of 1.5. All right, let's see. Yeah, I think we can surely subtract the equation in this case. I'm going to subtract just like column subtraction in primary school. But we do left side minus left side. So 17.6 minus 11.9. What should we get there? So that's 5.7, isn't it? Yep, okay. And then a cancels out. And then you have minus b. And then 4 to the power of 1.5 minus 9 to the power of 1.5, yeah? Yep. So b would be equal to 5.7 or divided by minus, because I'm taking minus as well, 4 to the power of 1.5 minus 9 to the power of 1.5. All right, let's do a calculator here. 5.7 divided, hang on. 5.7 divided by minus, brackets, 4 to the power of 1.5 minus 9 to the power of 1.5, right? Hang on. Yep. So that's, nice. B is 0.5. Okay, so we should find A using this value. So A would be then, just going to use the second equation. So 11.9 plus B, which is that, times 9 to the 1.5. Okay, so I'm using this one to just find B. Sorry, A. Let's see if I plugged in everything correctly. Yeah, I'm very careful. 11.9 plus 0.3 times 9 to the 1.5. Nice number. Good sign. Yeah. Yep, happy with that. Okay, so the full equation, don't forget, is 20 minus 0.3 t to the power of 1.5. Okay, that's the full equation. All right. Part B, find, according to the model, the height of the bird's nest above the sea. Okay. So because the birds start from the nest, so that means we got to find the height when they start. which is at t equals 0, right? Yeah, because t seconds is the time after the bird leaves its nest. If t is 0, then the birds are still at the nest, right? Okay, so we just put t equals 0 here. So we get h equals 20 minus, so if we put 0 to t, that's going to be 0 to the power of 1.5, so that's going to go to 0. So it's 20 meters here. Yep, 20 meters. Do we got the right units here? Yep, h meters, yeah. The limitation on the value of t. Okay, so, right. The capital T here is sometime after, right? And let's see. So, okay. I think there is a range here because if you look at the terms here, it's a negative. That means if you increase the time, there will be a point where height is less than 0. So the bird is like sinking under the sea or something. Yeah. So if we equate 0 to h first to find that point, yeah. So it's 20 minus 0.3 t to the power of 1.5, right? Because they haven't told the value yet. Here we gotta solve for it. So t equals 20 divided by 0.3, and then to the power of, well, or root 1.5, like that. Yeah, you take 1.5 root order of that. Well, that's possible. Yeah, we can do that in the calculator, just like, well, let me show you. Well, hang on. Yeah, like this one. 1.5, and then that'll be 20 divided by 0.3, like that. So that's about 16.44 meters, right? Sorry, not meters, seconds, right? Because that's time. Well, that's telling you that the birds, this whole model, can only model up to about 16 seconds. That's just, you know, you take longer to go to a toilet there, right? 16 seconds there, just like a couple of breaths actually. So here the limitation on the value of t. So the value of t equals 16.4 here. It only hang on. Let me think the wording here. So this value limits the height of the flight. Okay, so I think beyond t equals 16.4 second, the height of the bird is negative, which is not realistic. That's one point I can think of, but if we talk about the value of 16.4 itself, it's probably too short. Like the model is too limited to just a very narrow window of time. And 16.4 and the range of 0 to t to 16.4 is a very small time window to model the flight of a bird. That might be a bit subjective, but why would you model something just knowing it by just, you know, like 16 seconds and that's it? Probably not that useful, right? So yeah, I think that would be my answer there. Number 7, what do we have here? Graph, at least. Figure 1 shows a sketch of the curve with equation y equals fx, where fx is a quartic. So quartic is like degree 4 for the polynomial. The curve has a maximum turning point at that, and that crosses the y-axis at that. Okay, yeah, everything is in the graph now. Has minimum turning point at x equals 2. Yeah, minimum turning point here. Find a set of values for which the derivative of fx is greater than 0. So we probably don't need to differentiate anything because we don't know the graph yet. We can just look from the graph directly. You got to understand that because f dash x is a gradient function. This is a gradient function. So to have f dash x greater than or equal 0, this means increasing function, right? It's an increasing part of the function here. Not all of them is an increasing function. Not all of the line is an increasing. So like here, if you look at the left part here, like when x is less than -1 to the left, this is increasing because when you go to the right, the line is increasing. So we have one first, like x less than equal -1. Yeah, we got to include the -1 here because the gradient includes 0, so that indicates turning point. So we got to include x of -1. Now, what about the next part? Well, this part, gradient is smaller and smaller, as in getting more and more negative, right? This is negative gradient, so it's a decreasing function. The line is declining. Until this point, x equals 2, the gradient is rising again, and you have an increasing function because the value of y increases. So you're going to have x greater than 2 now. And does it go forever above 2? Well, at this point, after 5, it's going to decrease again. So we're going to cap that to just x less than equal 5 greater than equal 2, like that. Do we have to do set notation? Yes, we do. Okay, so the answer to x would be x, yeah. And then we have x less than -1 union, yeah, x, where x is less than equal 5 greater than equal 2, like that. Yeah, you got a union there. Okay, there you go. That would be set notation for the whole thing. All right, and that's it for part A. Part B, find the set of value. Find the equation of C. You may leave your answer in a factorized form. Okay, easy now. We know that when we have a quartic, like, okay, let's go back to a simpler one like cubic, right? When, for example, you have a cubic like this, when you have a turning point touching the x-axis, of course, okay, we know that when the line crosses the x-axis, that's going to be one of the roots. For example, if this is -2, you know that one factor is x plus 2 in the factorized form of the function. But what if the turning point is touching the x-axis? Let's say this is 3. Well, you know that that's going to be x minus 3 squared. If this is a cubic, of course. And it is, just by the drawing there. But now you have a quartic where the turning points, 2 of them, touch the x-axis. So the same concept apply. We're going to have x plus 1 here squared, and the other one x plus minus 5 also squared. That's it. That's really it. Yeah, I mean, yeah, if you plug -1 in, you get 0. If you plug 5 in, you get 0. We can try if we are not happy. Yeah, we should try because I don't know the a constant here. There might be an a constant here. So I'm going to put that first. Let's put it to fx. Now, there might be an a because, you know, by having a different number for a there, doesn't change where the turning points touch the x-axis. So it could be a 2, it could be a 10, it could even be a million or whatever, right? So we need to use the other information here, the y-intercept. So if we plug x0, we're going to get -75 to find the value of a. Yeah, so I'm just plugging in everything here, basically. See what we got for a. And a turns out to be what? -75 divided by, so that's 1 times 25, so that's 25 basically, so that's -3. See, if you didn't try that, you wouldn't have known, right? That it doesn't have to be 1. So now I can conclude that the fx is just -3. Well, it makes sense because you have a inverted quartic shape there. I mean, if it was a positive, it should be like this, a W shape. Yeah. And then we write down everything. All right. And that's all it is, right? Okay. Yeah, I leave it in a factorized form. Yep. So part C. The curve C1 has equation that plus k, where k is a constant, given that the graph C1 intersects the x-axis at exactly 4 places. Right, so how do we make this curve cut at exactly 4 places? This is only 2. So, okay. Alright, so find the range of possible value of k. Alright, so I'm going to draw that shape quickly here and illustrate to you with some animation maybe. So if you only have, let me see the actual graph, okay. If you have something like this is the fx, right? It only cuts the x-axis at 1 point. Yeah, but we want 4 points. So how about we move up? If we move up only slightly, do you see there's already 4 points there? Yeah, already 4 points here. Let's count. 1, 2, 3, 4. That's all we want, 4 points. But we can't move up to forever, because if we keep moving up, that's going to be more points, like this. Wait, hang on. That's 4. Oh, sorry, I meant less points. So if you move up to this point, you only got 1, 2, 3, because you touch one of the turning points touches the x-axis. So from 4, you have less. 4 is the maximum number of intersections in a quartic. So cubic maximum 3, quadratic maximum 2, linear maximum 1. That makes sense, right? So quartic, because it's degree 4, so maximum number of intersections with the x-axis is just 4. And here we have less. And if we go up more and more, it's going to be 2 forever, right? Imagine I extend the 2 lines down, it's just 2. So this is the range. You got to be greater than this, and you got to be smaller than this, right? This is the range here. That's the boundary. That's another boundary there. All right? So k has got to be obviously greater than 0, right? Because if k is 0, you're going to have this same shape. That's not shifting anything. So k has got to be greater than 0 to shift it up ever so slightly. But k cannot be greater than this length right here. Okay, because if it's greater than that, it's going to shift up by more than that amount, and it's going to start having this turning point touching here, which will lead to just 3 intersections. So we're going to have k less than some value. I should flip the thing, right? So k greater than 0 and less than what? So what's that? Okay, we need to find this coordinate of the turning point, right? Because by that we know the height here of the well, if you know what I mean. So we're going to plug 2 because it gives here 2, yeah? So we're going to plug 2 to fx to see what that gives you. So I'm just going to do f2 here, yeah, equals minus 3. So 2 plus 1 is 3 squared, and 2 minus 5 is minus 3 squared. And that is equal to, should I use a calculator? It's just 9 times 9, right? Is 81. 81 times 3 is 24. 243 is a minus. Is that right? 9 times 9, 81. Yep, I think so. Okay, so it's telling you that the shifting amount cannot be greater or equal to that. So it's just 243, because we are talking about positive shifting here, so it should be a positive number there. The range of possible values of k. So that's it. That's it. So that's the answer there. It doesn't require set notation, so I'm done. All right, that's it. 81 times 3, yeah. You see, I'm weird. I don't like using a calculator, but then I just like I have to check my mental math a lot of times. Maybe I'm too careful. Okay, I still make silly mistakes. Anyway, number 8. A student was asked to prove that the square of any number can be expressed in the form 5n or 5n plus or minus 1, where n is a natural number. So that special n character there is depicting natural number. The start of a student's proof is shown in the box below. Let m equals 5k. Consider, yeah, okay, so we have square of any number can be expressed in the form 5n or 5n plus or minus 1. Right, okay. So because we want to prove, so basically the statement is asking you to prove whether a given square number is a multiple of 5, because 5 in there, it's a multiple of 5, or a multiple of 5 plus 1. That's basically what it's saying there. Because of that, that's why the start of the proof, you must, it's probably better, it's best practice to assume that we're going to have a square number by just squaring some multiples of 5. So any number, we can put it to a multiple of 5, a multiple of 5 plus 1, a multiple of 5 plus 2, a multiple of 5 plus 3, and a multiple of 5 plus 4. That also works for odd and even, because odd is 2n plus 1 and even is 2n. That can also work for a multiple of 3, so you would have 3k, 3k plus 1, 3k plus 2. Yeah, so that's why it's starting from 5k and go to 5k plus 1 and 5k plus 2. Now we just have to check for the errors, right? Okay, so there is an algebraic error, so m squared, 5 squared, okay, 25k squared, 5 times 5k squared, that's 5n, where n is 5k squared, so that's fine, yeah. Let n be 5k plus 1, so that's expanding. So 5k squared times 2k plus 1, yeah, I believe that's fine. Pulling 5 out here, we get that, plus 1, yeah, 5k plus 1, where n is that. Doesn't seem to be any error there. Let m be 5k plus 2, then m squared would be 5k, yeah, so this is 2 times that. Is the 10k here, that is wrong. Okay, so the error is the last line. M squared equals 5k plus 2 to the n, 2k squared plus 10k plus 4. This one is wrong, but it should be, yeah, identifying correct. 5k squared plus 20k plus 4, just that one. Yeah, because 2 times 5 times 2 is 20k. Okay, we correct the whole thing then. Yeah, so, and then we have m squared equals, so that would be 5 times 5k squared plus 4k, yeah. Interesting. Hang on. It's shown in the box. All right, yeah, okay, so that's fine. We keep the plus 1 here and minus 1, because this is, oops, sorry. This is telling you that you can do plus or minus 1. So this works, right? Let me just check my math again. Yeah, 5 and then you get 4. All right, that's fine. So so this is 5n minus 1, where n is 5k squared plus 4k plus 1. Yeah, so that's part A done, right? That's it. Part B, show the calculations and statements that are required to complete the proof. Right, so we need to do 2 more cases. So just going to copy the template there, easier. M be 5k plus 3. So consider m squared, right, equals 5k plus 3 squared. So we have 25k squared plus 2 times 5 times 3, that's 30k plus 9, yeah. So that's going to be 5k squared plus 6k. Well, let's do 2 here and then minus 1 out here, yeah, and this is where n equals 5k squared plus 6k plus 2, yeah. Okay, and then the other case is just letting m equals 5k plus 4, and that's the last one. You can't have 5k plus 5 because that would be a multiple of 5. We already did it, like they already do it for you here, so we just up to this one, yeah. Consider m squared equals 5k plus 4 squared, so that's equal 25k squared plus 2 times 5 times 4, that's 40k, and plus 16, right? So that's going to be 5k squared plus 8k. Well, let's do 3 and then plus 1 outside like that. Nice, okay. So this is where n equals 5k squared plus 8k plus 3. Okay, and the statements, right? So for all n being a natural number, no, hang on. For all square number, yeah, for all square numbers, this is basically m. No, for all square numbers m squared, they can be all written in the form 5n or 5n plus minus 1. We have shown that all of the cases work, right? Yeah, all of them. Therefore, the statement is true. So the square of any number can be expressed. Oh, hang on. I should write also where n is natural number here. Yeah, can be expressed in the form 5n or 5n plus or minus 1, where n is that. All right, just repeating, a bit tedious there, but you probably have to write it to get the marks there. And that's question 8 done. Oh, question 9 is a bit long. All right. Question 9. A racing car is driven along a straight road. Okay, figure 2 shows a graph of the speed of the car, VT graph here, as it travels along the road. The car starts from rest and is driven for t seconds. All right, this is similar to the flight of the bird there, before stopping. The speed of the car is modeled by this equation. Okay, exponential now, where t seconds after the car starts to move. According to the model, A, find the value of t, giving your answer to 1 decimal place. So we just equate the function here to 0 because we want to find the x-intercept, basically, to find the value of t. Yeah, so 0 equals 115, 15t minus t e to the power of 0.2t. Interesting function there. So if we move one term to the other side, we're going to have this, right? Yeah. And of course, t can be equal to 0 now. So if I just cancel t out, I have this. And I know that, okay, t is 0. One of them is 0. Yeah. T equals 0 here is one of the solution because we cancel it out. Now, we solve for t here, so it's just ln 15. If you reverse the e there from the right side, then I bring 0.2t down, so t equals just 1 over 0.2 ln 15. If we want to simplify that, well, there's just one decimal, but I'm going to have a simplified form first. So 1 over 0.2 is just 5, right? 5 ln 15. Okay, but they want 1 decimal place, so it's just going to be 5 ln 15, which is 13.5. Yeah, so the big T equals 13.5 seconds. All right, so that's the answer to part A. Easy. Part B, show that maximum speed of the car occurs when t equals that. Maximum speed is a turning point here, right here. Okay, so well, because this is far from quadratic, it's not quadratic. I mean, if it was quadratic, we would just do midpoint between 0 and capital T. But this is not a quadratic function, so we need to differentiate anyway. So let's differentiate dv by dt. Well, that would become acceleration, physically speaking, but anyway, this is math. So differentiating the first term is 15. Yeah. Differentiating the second term requires product rule. So u, which is t, the first one, dv, so 0.2 e to the power of 0.2 t, yeah, that's u dv, plus v du. So du is 1, so we just write v as that. I gotta be careful with my handwriting here, yeah. Okay, so that's the differentiated form. And we want to equate this to 0 because that's the turning point, gradient being 0, all right? So how do we solve this? All right, okay, so let me move 15 to the other side, or basically just having 0.2t, and then factorize in the brackets there as well. So I'm going to have e to the 0.2t, well, hang on, I should be factorizing e to the 0.2t outright, and here I have 0.2t plus 1 equal 15. Okay, basically just moving one of the big terms to the other side. So, well, not e to the 0.2t, okay, hang on. Interesting. So, oh, I thought we were solving for this. I'm just gonna have to show that and use numerical method. All right, yeah, because solving this is a bit impossible here. Okay, so let's see what we need to do, right? Okay, all right. So because there is an ln there, so I feel like I need to move this to the other side so that I can take the ln, and it would make the e disappear there, like this. And then you see that when we take ln, then it's gonna make it work. Now, we probably have to simplify the fraction here first. So like the 0.2t here is actually 1 over 5, right? So if I have 1 over 5 here, I'm going to multiply 5 on top and bottom. How about that? Yeah. So I'm going to have 75 here divided by, because I want to cancel, yeah? I want to cancel the 0.2, so this would become t plus 5 instead. Yeah, just in the brackets there, we want it. So if I take ln on both sides, I get 0.2t equals ln of all that, right? And if you divide by 0.2, it's going to be just multiplying by 5, same thing. So we get that, which is as required. That's good. Okay. All right, so that's part B done. Now part C, let's do it here. Using the iteration formula, t of n plus 1 equals all that, with t1 equals 8. Part I, find the value of t3 to 3 decimal places. Okay, so we're going to do, so I probably need to write for t2 first. So t2 equals t1 plus 1 equals 5 ln 75 divided by t1 plus 5, like that. Yeah, and then we're going to, so because they want it to t3, so I'm going to do 8, store it first. I have an experience on this calculator. I'm going to use this one because it's better for numerical. Somehow, I don't know. So 8 equals as an answer, and then clear 5 ln fraction 75 divided by, what's that, answer, right? Yeah, answer plus 5, close bracket. So that would be t2. Yeah, 8.762669. Yeah, I'm gonna stop there. And then if you press equal once, it's just gonna store. It's not gonna be t3 yet. Press it again, that's t3. 8.478. Yeah, 3 decimal places. All right, that's t3. Alrighty. And we're going to keep it because in part I think we need to keep the iteration going. Okay, so we're going to keep pressing. I'm guessing still in 3 decimal places, so we're going to keep going until the third decimal doesn't move. So it's 554 then, right? So t is 8.554 second. Yeah, is it seconds? Yep. Yeah, so that would be the answer, guys. All right, because we keep pressing the calculator and the third decimal stops here. Okay, so that's it for that question. Number 10. Was that number 9? Yeah, okay, it was. Number 10. Vectors. Given that PQ is that, QR is that, find PR. Well, PR, okay, we can think of PR as a relative vector coming from PO plus OR, like that. Or you can do OR minus OP. That's fine as well. But this would have been fine if you have the position vector of P and R, but we don't. So how about we just change the middle one here to anything we want? And the thing that we should change to is Q rather than the origin. And that should work as well. Yeah? So basically just adding those up, right? Okay, so just add them up there. Be careful about the coordinates and components. So I add I have 8i. J doesn't have the J for the other one. Yeah? And then K just plus 4K. Gotta be careful there, guys. Okay? So that's it for PR. Hence show that triangle PQR is both right angled and isosceles. Well, you need to show two things. PQR. So let's find the size of PQ first and see. Yeah. So PQ is square root of 2 squared plus 8 squared plus minus 2 squared. So that's going to be what? Just calculator, maybe the other one. Okay, square root of 4 plus 64 plus 2, that would be root 70. All right. And square root of QR, yeah, is square root of 6 squared plus 6 squared, that is square root of 72. So that's not the same as 70, so we need to do PR as well. PR, square root of 8 squared plus 8 squared plus 4 squared. Okay, it feels weird here. Isosceles? Oh, maybe this is root. Hang on, let me find out. 64 plus 64. Okay, this is 12. Right, guys. Is both right angled and isosceles? Well, PQR. PQ, QR, PR. That should be two pairs, like one pair of equal sides. Hang on, what am I missing here? 36 plus 36 is 72. That's 4 plus 64 plus 4. Oh, hang on. I don't know what happened there, but the first one was wrong. Yeah, I think I pressed the calculator wrong. I think that is, yeah, that should be 72. This one, sorry. Yeah, see, I make a mistake. I correct it. Because it feels weird to not have what they want here, so I just check my calculation again, and that is just fine. I mean, you guys would have done it too. So we know that PR equals QR now is an isosceles. And to prove it a right angle, right, how about we do Pythagoras? So assuming that these two will be the legs of the right angle triangle, like this is 72, root 72, yeah? So we're going to do Pythagoras. So root 72 squared plus root 72 squared equals 72 plus 72, which is 144, which is, 12 squared. Therefore, PQ squared plus QR squared equals PR squared. Therefore, PQ equals QR. This is isosceles as two equal sides, yeah. And P, is it PQ and QR? Yeah, PQR, right? PQQR, yeah. PQR equals 90. Yeah. This is right angle. Right? Since Pythagoras works. Yeah, since this. Right? So, yeah. I proved it. Okay. That's done. All right, so number 10 is done. Number 11. The value of car in V pounds is modeled by the equation. Okay, a lot of modeling here, where A and K are positive constants and T is the age of the car in years. Given that the initial value of the car was 20,000 pounds, the value of the car was 12,000 pounds when it was 2.5 years old. Part A, find the complete equation for the model giving the exact value of A and the value of K to 3 significant figures. All right, yeah, we're going to use the equation, plug in the conditions there and get simultaneous equations and solve for A and K, right? Is it? Yeah. So initial value, the initial value is when T equals 0. When T equals 0, right? V equals 20,000. Yeah. So that would make this equation like plus A like this. Yeah, because e to the power of 0 there would be 1. So we have the A value there. So A is just what? 18,500. Like that, yeah? Yeah, I think that's fine. Okay. Pounds. Okay, so that's A. And then the value of the second condition, yeah, we now got A, so we just find K. So the other one is 12,000 equals 1,500 plus that times e to the power of minus k times t, where t is 2.5, like that. Just subbing everything in, yeah? Yep, okay. So e to the power of minus 2.5k is just subtracting 1,500 from 12 there, I get 10500. Yep. And then dividing both sides by this, yeah, that would be e to the minus 2.5k. So k itself is going to be ln of this, right? Ln of that, and then divided by minus 2.5, just solving the equation there. So we want 3 significant figures for k. That's fine. So fraction, ln, fraction, 10500, 18500, close bracket. Down here we have minus 2.5. So that's going to be 0.2236. So 6558. I'm going to write that first and then round it to 227. Okay. All right. So that's part A done. Oh, find a complete equation. I almost forgot. Yeah. Because I made that mistake before. Like they asked you to complete the equation, but I just wrote the K and the A in this case. Would have been. So that's 18,500 e to the minus 0.227 k. Wait, no, t. Yeah, because it's a function of t there. All right. So that's it for part A. Part B. Show that the rate of change in the value of the car can be expressed in the form. The rate of change. Okay, they would like this kind of question as well. In some years, the form is actually worse. So basically, we're just gonna differentiate the car price. The big V by dt is just basically. I'm just gonna differentiate the initial form first because I don't want to write too much there. It's just so the 1,500 goes away, and we have minus ka, just bringing the minus k down to multiply a, and then e to the minus kt. Okay, now you gotta be careful here. I mean, I wouldn't, this is the tip, I wouldn't just substitute a and k in yet, because look at the form they want. There is no exponential there, right? So if we go from the original equation and make at least a to the e, a times e to the power of minus kt the subject, yeah, a times e to the power of minus kt the subject, you're going to have v minus 1500. And we can sub that into these two guys there instead of that, right? So we're going to have minus k and sub that all in, v to the all that. So I haven't written any a or k yet because we don't need to. And that is actually exactly what they want. Just 2 lines, right? That's it. So the tip here, when you deal with exponential, don't need to sub in all the values yet, like the constant terms. Just keep working on the, the form where there are still unknowns. That should be fine, all right? Okay, and C, state the limitation of this model. All right, okay. So the limitation might come when you maybe make t approaches infinity like that. So if t approaches infinity, the e to the minus kt will approach 0. So value will approach 1500. Yeah, it can't go smaller than that, can it? Yeah, so the limitation of the model will never, so the value of the car will never be smaller than 1500 pounds. If you bought a car and, leave it for maybe 100 years, let's say you can live that long, or okay, let's say 60 years. All right, let's say it's the car from your, puberty, and then you bought it and then kept it for 50 years until you're like 60 or 70 or something. And would the car value be still 1500 pounds? I mean, imagine that would be just a piece of metal, right? Probably useless. If you don't change anything of the car, maybe useless. Everything will be broken, right? So I'm just going to say the price, the value of the car, never can never be smaller than 1500 pounds. So not realistic. Yeah, just gonna say that because that's just 1 mark, so that's a limitation. Yeah. Okay, number 11 is done, and number 12, a graph again. We are at 1 hour and 6 minutes, so I think we're fine. Figure 3 shows a sketch of the curve C with equation that. All right, interesting. We have a lot of lines here. The straight line L with equation that. Okay, so we have 2 functions here, the curve and the line. Verify that C and L intersect where x equals 6. Verify, not show. Verify means you can plug 6 in the 2 functions and get the same y value. Yeah. So at x equals 6, I get y from the curve 15 times 6 divided by 2 times 6. We just need to show the working here, yeah. Just the plugging in there basically. So 15 times 6, and what's that? 12 plus 3 is 15, and then times 3. So that's 2, okay. And then the other one is 2 times 6 minus 10, that is also 2. So at x equals 6, y coordinate of the line, I'm just going to do yc because the curve is named C and the line, which is L, is equal. Therefore, they intersect at x equals 6 because they have the same y coordinate at that point, right? Part B, the curve and the line also intersect at the point Q shown in the figure. Okay, down here in the 3rd quadrant. Show that the x coordinate of Q is the solution of that. All right, so basically we equate them, right? So we equate y curve equals y line, yeah? So we have 15x divided by all that equals 2x minus 10, all right? Well, by the looks, right, let me see, okay, I can simplify, is there a point? Yeah, okay, so it's 15x, and then I have 2 here, x minus 5, and then I probably have to maybe multiply out all of the terms and the brackets like that. Yeah, okay, a bit tedious there, but you have to do it, I guess. Okay, so let's keep 2 out here, and then I'm gonna do these two first. So x squared minus 8x plus 15, yeah, and then the 2x plus 3. I did those first because they're easier just to start with. Yeah, and 15x equals, okay, so I'm gonna keep 2 here again. The first times the first is 2x cubed. The first times the second is 3x squared. The second times the first is minus 16x squared. The second times the second is minus 24x. The third times the first is 30x. The third times the second is 45. So I should get 6 terms, yeah, because 3 times 2 is 6, right? Yeah, so I'm happy with that, I think. And you need to add them up and multiply by 4 in. So I have 4x cubed here, the only term. And then for the x squared, I have minus 13. So that's minus 26x squared. Is that? Yeah, we have that. And then for the x term, we have 6x in the brackets multiplied by 2 would become 12x. And then you subtract 15x from this guy. Yeah, you have minus 3x, right? Yeah. And then that would be 90 for the number term. Yeah, doesn't matter which side you write, it's fine. Yeah. Okay, so that's as required. Part C. Using algebra and showing all the stages of your working, find the exact coordinate of Q. Algebra. All right. Yeah, we already know that one of the solution is at x equals 6. So that means x minus 6 is a factor. It must be a factor of this. Yeah. So 4x cubed minus 26x squared minus 3x plus 9. Because we know that one of the intersections must be at x equals 6. That is the great help, right? Although it doesn't use the word hence or something, or use the answer to part A or whatever, we need to know that. And that's important. So again, you can either do a long division or a short division or even factorizing. Now this time I'll try something different. Yeah, let's do factorizing, right? So we're going to do x 4x cubed minus 26x squared minus 3x plus 90. So I'm going to put it equal to x minus 6. And then because the other factor should be quadratic, right? So I'm going to have to write ax squared plus bx plus c. This one, if you know how to do, is also easy. Yeah, let me show you. So like, you know that the first term times the first term must be 4x cubed because it's the only pair that would give you the cubic term there, right? Because it's the 4x cubed. So a must be 4, logically speaking, yeah? So a must be 4, yeah? Is that good? And then the last term times the last term, minus 6 times c, should give you the last term. And that's the only pair as well, right? So c must be, okay, I do 90 minus, divide by minus 6, right? Because you have 90 equals minus 6c. So that would be that. It's just minus 15, isn't it? Yep. Now we got 2 of them already. Now for b, you just pick another degree. So let's do x because the number here is small. So how do you get x from the multiplication? So that x needs to multiply c, right? Yeah. So I would have minus 15x, right? Yeah, just pairing these two. And the minus 6 must multiply the bx. So minus 6bx, yeah, must be equal to minus 3x, like that. If you solve this, we're canceling all the x's, you're going to get b. So b must be equal to moving the 15, so you get 12 divided by minus 6, so that's minus 2. Yeah, is that okay? Let me double check my work. 12 minus 6, yep, so b is minus 2. So that means that whole thing will be factorized as 4x squared minus 2x minus 15. I'm just looking through the ABC there, basically. And can we factorize this further? Well, it seems like we can because they cut at 3 points, so that should be 3 roots, basically. So let me just, try factorize that, right? Okay, using my brain. So how about, I'm gonna go with 4x and x first, maybe. Because, that would give you the first term. Now, minus 15, how about minus 5 and 3? Minus 5 here and 3 here. Nope. 3 here, minus 5 here. Nowhere close. So let me try 2 and 2 now. Okay, 2 and 2 instead, I think. Must work, it must work. So 5 here and 3 here. 5 here and 3 here. I gotta get some puzzle here, guys. I'm gonna be back. The time is still on, it's fine. All right, I'm back. Sorry about that. So 5 and 3, 10 and 6. Nope, 5 here and 3 here. Wait, hang on. That's the same, right? Ooh. Seems like I need to use a calculator, guys. 6 and 10. Doesn't give 2. Is there something wrong? Let me just check by a calculator. 4 minus 2 and minus 15. Yeah, all right. Exact coordinates of Q. All right. This gives me a bad sense. Okay, let me double check my work because it feels like if I don't get nice numbers here, I might do something wrong. So is it this factorizing work? So because we got a 6 there already. Yep. Let me check this, yeah? So if I multiply this, I get that. I multiply with the x squared, so that's minus 24. And minus 2, so that's minus 26. Yeah, this one is okay. This is 90. Yeah, this one is good. And the x term is minus 15 and plus 12, so that's minus 3. Everything is fine. Everything is fine. I guess that must be it. That must be it. That must be okay. So we're gonna have to get that this one. X equals minus 2 plus or minus square root b squared minus 4 times a times c, yeah, all divided by 2 times a, yeah. And then we're just going to write the answer. We just pretend like we try to work on that using the formula, but actually we just use this. Yeah, so that's I guess root 61 plus 1 over 4. That's a minus. What's the other one? a plus, right? And a plus like that. Yeah, let me check. Yep. Okay, now the trouble is we need to sub this back to get q. So the q value is where x is negative, so this is xq. So xq is going to be that. Yeah. Oh, that's the exact coordinate of xq. We're done, because I thought it was asking to find the points, like the y coordinate as well. So I think we're good here. That is just the answer. All right, next part, number 13. I think we're almost done here with the whole paper. Okay, so show that the integral of that is 2 over 25. All right, let's see what we can do here. This is pure 2, right? Sorry, pure 1, but A2 level. So we can do by parts, for sure. We can do by parts. We can do by parts. So let's do by parts. So this is integral 2, and then x, 2x plus 1 to the power of minus 3 dx. Yeah. So I'm gonna make this u, make this dv, because we can. And then that's gonna be equal to u times v. So v would be, you integrate this, right? You integrate this, you would get the same thing to the power of power added by 1, so you get minus 2, but you have to divide using reverse chain rule by 2. Yeah, so you get that. All right, that's just the way it is. Oh, divide by minus 2 and also multiply 2. I forgot to divide by the added power minus 2, and you have to divide by the derivative of the inner function here as well. So that is basically minus 4, or I write minus and 4 here. Yeah. Okay, so that's going to be 2x. So this is going to be minus, right? So 2x plus 1 over 4 to the power of minus 2. Okay, and minus integral of duv. So du is 1, we just don't write, just 1 there. And v is again minus, right? So it's a minus here, that's why I'm going to change this to a plus and just write 2x plus 1 to the power of minus 2 divided by 4 and dx. Yeah, so that's going to be minus x divided by, I'm going to move that down here because it seems more convenient like that. Yeah. And then this one, well, integral of that is again using power rule. We're going to have 2x, we have 1 over 4 here, and then 2x plus 1 to the power of minus 1 divided by minus 1, and then multiply by 2 again, reverse chain rule with the added power. So that basically is going to simplify to minus 1 over 8, right? So I write minus 1 over 8 like that. Yeah. Okay. And that's everything. So if I put the bounds from 0 to 2, so I'm going to have minus x divided by 4 2x plus 1 to the power of 2, and then minus 1 over 8 2x plus 1. Yeah, and put the bounds in 0 to 2 like that. So you're going to have what? Okay, so if we put 0 in first, just consider 0 first. Well, yeah, we have something, so we're going to do both. So that's going to be minus 2 divided by, okay, so 2 plugging in the brackets down there in the first term, we get 5 squared, right? 5 squared is 25, 25 times 4 is 100, so that's 2 over 100, minus the second term is 1 over, 8 times 5 is 40, yep, okay. And that's going to be minus, yeah, I do brackets here just to be safe. 0 subbing in the first term is going to disappear, but the second term you're going to get minus 1 over 8, right? So we're just going to use the calculator there. Go to the calculator mode. Minus, what was it? 2 over 100 minus 1 over 40, and then plus 1 over 8. Yep, We got that? 2 over 25 as required. That's it, done. Yep. Next one, number 14. A. Show that sine of that equals sine of that plus root 3 cos of that equals that. Well, by the looks, it feels like we need to use additional formula here. Yeah, let's try that. So sine A plus B is sine A cos B plus cos A sine B. That's the first term, and I'm going to do that for the second term too, expanding everything in. So root 3, yeah. Cos A plus B is cos A, actually, no, that's fine, let's do it. Cos A cos B minus, I have expanded the root 3 in here as well, and then sine A sine B, right? So that's just left hand side equals that. Okay, let me double check everything. Cos A cos B sine A sine B minus, yeah, okay. Now we know that cos 30 is just root 3 over 2, so that's root 3 over 2 sine x, and sine 30 is 1 over 2, so 1 over 2 cos x, plus root 3 over 2 times root 3, so that's going to be 3 over 2 cos x, minus, this is 1 over 2 times root 3, so root 3 over 2 sine x. Yep. Now see, they cancel, so it simplifies to 2 cos x as required. Easy peasy, right? B. Hence solve for that. Okay, so hence, right, we need to use the answer to the previous part. Well, seems like the left-hand side is exactly the same thing as this, but changing from x to theta. So we're just going to write 2 cos theta there, because it's equals 2 cos x here. So this whole thing becomes 2 cos theta equals 3 sine 2 theta. All right. Well, yeah, we can do double angle. So 2 cos theta equals 3 times 2 sine theta cos theta there. Okay? And yeah, you can cancel the 2 out, but if we move everything on the same side, we could cancel cos theta, but you're going to omit the answers to cos theta equals 0, sorry. So I don't think you should do that, because, I mean, if you are aware that it's going to give you some solution, then cancel and just say in your mind that cos theta can also be 0. In this case, yeah. Now, clearly, if you factorize cos theta out, you're going to get 1 minus 3 sine theta, right? Like that. See that? So yeah, because this is just A times B equals 0. So A could be 0 or B could be 0. Yeah? So cos theta equals 0, or 1 minus 3 sine theta equals 0. Like that. Okay? And theta is already in the right range there, because we are solving for theta here. So for cos theta equals 0, so cos of what angle equals 0? Pi over 2, right? So for this one equal pi over 2. Well, we do in degrees, so it's 90 degrees. And then it could also be 270, but that's out of the range, so we're just going to take one value here. And this one, or theta equals, well, hang on. Let's just do sine theta equals 1/3, like that. So we're going to get the first quadrant and the second quadrant, right? Yeah, so we just do arcsine. So in degree already here, arcsine 1 over 3, yeah? So theta would be 19.1 decimal place, so 0.5. And I'm just going to do 180 minus that, because we know that the other one is 180 minus that in the second quadrant, yeah? And that's it, I think, because we can't go the third quadrant. It would be the negative value of sine. So, and 160.5 for that. Yeah, that's it. So that's all the answers. 3 answers there. Yeah, 1 decimal place where appropriate. So we don't need to do that for 90 degrees because it's exact. Okay, that's done. Still have a lot of time there. This is probably the last one, I guess. isn't it? No, not yet. Okay, there are 16 questions. All right, this year. Okay. Number 15. Figure 4 shows a plain view for the design of the stage. The shape of this design consists of a sector of a circle AOB joined to a rectangle OBCD. OBCD. All right. The radius of the sector is r meters and the angle OAB is theta radians. Okay. AOB. All right. The length and the width of the rectangle are r meters and 1/10 r meters respectively. Total area is that. Show that the perimeter of the stage P is given by that. All right. So basically, we are given that it is theta radians, but the form in part A doesn't have any radian. It means that it implies that we should eliminate theta with the given information here, which is the area of 240, right? So if you equate the area to, like you try to find the area from the whole shape. So it's going to be the area of the rectangle being r times 1/10 r, right? That's the rectangle, easy. And the other part is the sector. So it's 1/2 theta r squared, isn't it? Yeah? Because we get everything here, r, and then theta there. So that's the area of a sector where theta in radians, yeah? Yeah, so we're just going to solve for theta here, yeah? So theta equals, well, okay, let's just factorize r squared out here first. So I have 1/10 on the first term and theta over 2 here on the second term, right? So 240 here divided by r squared would be equal to 1/10 plus theta over 2. So theta alone is just 240 divided by r squared minus 1/10 and then all multiplied 2. Just moving bit by bit to the other side to make theta the subject. So you would have, yeah, let's keep it in that form, yeah? We don't need to simplify because they don't ask for theta. Now, perimeter, yeah? So you could find perimeter by doing r theta, right? So arc length S, yeah, is r times theta, which is r times all that, right? I'm just going to write down like that. Okay, and then that's the arc length, and then the perimeter would be equal to the arc length plus you have BC there, right? BC here, and also OD there, so it's 2 times 1/10 r, yeah? And then one of this, radius. So DC is going to be equal to the radius, and you have to plus another OA, which is another radius, so that's just 2r. OA and DC together. And that's it. So we just simplify that. So 2r, yeah, and all that, plus 2r times 1/10 plus 2r. See something? I can factorize 2r and put everything into the big brackets. Yep, would be faster, I think, like that. Yeah, because there's 2r here, 2r here, and 2r here. So in the brackets, so they have 2r, yeah, the 1/10 cancel. And if we expand 2r in, we're going to get 480 divided by r for the first term. And the other term will just be 2r. Yep, that's done as required. All right. And then part B. Using algebraic differentiation, find the value of r for which p has a stationary value. So we just do dp by dr, yeah? dp by dr equals, well, 2r becomes 2, and then 1/r, we differentiate 1/r, we get minus 1/r squared. So that's going to be minus 480 over r squared, right? Yep, okay. So if we equate this to 0, yeah, we're going to have 480 divided by r squared equals 2. So r squared equals 240 if you move the things there. And r is just, it can't be negative, so it's just going to be root 240 there because r is a radius. Yep, so we're just going to keep it as a surd. So that's what, is it some kind of square number multiplied by another number? Let's see, it's probably not. Maybe 36 will do, but okay, yeah, 4 root 15, whatever. Okay, and then equals 15.5. Okay, so that's my answer. I'm gonna keep two values there. Okay, I mean, as you can see, it's like a bit vague there which one is the right one, but you know, it really depends on which one they look for. If they want the third one, then yeah, go for it. If they want the decimal one, yeah, I have it. So that's like, you know, either one is fine. Okay. Yeah, we found the value of r for which p is stationary, and then prove by further differentiation that this value of r gives a minimum perimeter. Okay, so just by doing a second derivative, yeah, d squared p by dr squared again, just differentiating that guy again, we get 0 for the number 2 there, and differentiating 1 over r squared would be minus 2 over r cubed. So that's going to be plus 960 over r cubed, right? You pull 2 down, you get 960, and then the power subtract 1, yeah, you get r cubed. All right, yeah. So at r equals 4 root 15, d squared p by dr squared equals 960 divided by 4 root 15 to the power of 3. Well, surely that's greater than 0, right? But we're going to get the value anyway. Yeah. Okay. So that's 0. Well, we can keep the exact form there. Nice. So therefore, we can say that, well, because the second derivative is greater than 0, so this is a minimum. Yeah. Okay. Yeah. So we don't need to find the actual p minimum there. Okay. So we're done. Next, number 16. Yeah. All right. Figure 5 shows a sketch of the curve C with equation that y equals all that. The region R shown shaded in figure 5 is bounded by C, the line with equation x equals 1 and the x-axis. Okay, yeah. And the line with equation x equals root 3. So basically just this area. Use substitution x equals 2 sine u to show that the area is given by that. All right. It's good that they tell you what to do, right? So x equals 2 sine u. So by substitution, right, you just differentiate that substitution first. Then you're going to get 2 cos u, right? And make dx the subject because we're going to replace dx by something du. So dx is 2 cos u du. Yeah? So that means we're going to integrate the y. Yeah. So integral 1 over x squared root 4 minus x squared at dx from 0 to 2 would be equal to integral, we need to sub in the right bounds as well, 1 over, well, x squared would be x, okay, let me just substitute the dx by 2 cos u du here first, that's the dx, yeah? And then x squared down here, well, okay, let's just square this thing and put it in, so 4 sine squared u, right? And then in square root there, I would have what? 4 minus 4 sine squared u, right? Yeah? And let's put the bounds in later. Let's focus on simplifying this term first. You see there is a factor of 4 in here, so I can pull it out. Yeah? I mean, if I pull it out, I would get 2, and in the square root, 1 minus sine squared x, right? Follow? Well, this is cos squared, isn't it? From the identity. So this whole square root would be just simplified to 2 cos x. Yeah, that whole thing. So that is just basically 1 over 4 sine squared u times 2 cos u, sorry, not x. And we have a 2 cos u up here as well. So that's going to cancel the 2 and the 2 there, cancel, yeah. So I only have what? 1 over cosec right? 1 over sine, so that's just integral of 1 over 4 cosec squared u du. Okay, cosec there. And I believe, is there a formula for cosec squared? Let me just find in the formula sheet. I have it here. So let's see. Cosec squared, integrate cosec squared. We differentiate something, we should get cosec. Yeah, there you go. So we differentiate cot, we get cosec squared. So it means that if we integrate cosec squared, we should get a cot, because it's the same as if we differentiate tan, we get sec squared. So if we integrate sec squared, we get a tan. Yeah. So this is just basically 1 over 4. Because there is also a minus here, so it's a minus. Yeah. And then here would be a cot u. All right, is that okay? Yeah. But we don't forget about the bounds. Okay, let me show back the paper here. The bounds, right? So the bounds, well, x is 1. At x equals 1, then u equals what? Because the substitution here is 1, so we put x1 there. So sine u will be a half. That means u will be pi over 6, because sine 30 degrees or sine pi over 6 is 1/2. So u should be that. If x is root 3, so sine, so that would be root 3 equals 2 sine u, so sine u would be root 3 over 2, and sine of pi over 3 is root 3 over 2, so that's going to be pi over 3, which makes sense because it's to the right of the graph there. So this will be put to, so the lower limit is 1, correspond to pi over 6. The upper limit is root 3, corresponds to pi over 3, like that. Wait, hang on. I'm doing part B already? Sorry. I need to show that that is cosec. I should have seen that. I should have seen that they have cosec all along. But anyway, so let's keep this up here so that we say this is integral 1 over 4 cosec squared u du, and this is pi over 6 and pi over 3. Yeah? Wait, a minus sign as well. There you go. K is a constant to be found. Yep, minus sign. Wait, no, there's no minus yet because I haven't integrated. Alright, almost made a mistake there. Okay, yeah, it's going to be minus when I do part B. Okay? Hence, using algebraic integration, find the exact area of R, giving the answer in simplest form. All right, so R is just going to be put equal to this, right? Okay, so yeah, we already got the integration there. So that would be that. Okay, and then we just sub in the bounds, right? Not hard here. So you would have minus, I'm just going to take minus 1 over 4 out and then do the substitution in the brackets. So cot pi over 3 is so if you do 10 pi over 3, that's 1060, that's root 3. So this is 1 over root 3 minus root 3. Because 1030 is 1 over root 3. If you flip it, you get root 3. All right, so that's it. We want the exact value. Okay, so that's going to be 1 over 4 root 3 minus 1 over root 3. I just flipped the thing, yeah. 1 over 4. Now, if you do the fraction there, cross multiply that, you get 3 minus 1 over root 3. If I multiply that by root 3 over 3, where I rationalize the denominator, I'm going to get 1 over 4. So the top bit is 2 times root 3 here. So 2 times root 3 divided by 3. So that would now become 1 over 6, right? Because you can cancel the 2 and the 4 here. Root 3. Yeah, so 1 over 6 root 3. I can write root 3 over 6 as my simplified answer. Yep, so that is it, I guess, for the whole paper, 100 marks. So I'm done. So let's see. I mean, do I need to double check? Because I do that while I do the paper anyway. I always do that. But, you know, I still make silly mistakes. But if there was a question that I was uncertain about, I would go back. But I don't think there is anything. So I'm gonna stop the timer. Okay, so I have marked the paper and I totally nailed this paper. I got 100 out of 100. Although some questions I didn't need to write as much detail. But okay, let's do an overview on individual questions. Yeah. So number one, yeah, the tricky part here I think is part B, right? Well, there is another way to think about this. Yeah. So because if you look at fx, right? Because for part B, I'm talking about. If you look at fx, if you put f6, you got to understand that it gives you -4. Yeah, because basically when x equals 6, y equals -4, and you can write it like this. Yeah, good. Now, the algebra of function notation here we can use is to flip this one to the other side, so you can do 6 equals f inverse of -4. You can do that, right? So basically, yeah, when you have f inverse of 6 is -4, then when you have the inverse function f inverse x, then one point that lies on this curve would be -4, 6. Just basically that, right? So -4, 6 must lie on this curve, right? And when you reflect the point 6 -4, you're gonna have -4, 6. That's just one way to think about it. So you know, so if you put -4 in the f inverse, you get 6. So that's like x equals -6 and y equals 6. Sorry, x equals -4 and y equals 6 would lie on that inverse function. That's one way to go. So yeah, I guess that part is tricky. But anyway, for any point you are looking at, you can use the idea of, like the reflective property between the fx and the inverse. They should reflect. I mean, I guess if you draw it more accurately, yeah, not the way I did it, but more accurately, then it would have been easier. So if you maybe separate your scales more properly, like do the division more properly, yeah, like maybe like that, and then you plot, it's going to help you a lot, right, on this one. Yeah, maybe you should try that too. Just, doing the graph there to help you. Otherwise, it's fine. This one, yeah, the only thing to stress again is the part B here, where you have inside or outside the circle. So it's only inside when it satisfies the inequality where the expression part here is less than the radius, right? Less than the radius squared. Yeah, that's the thing to know there. So if you sub in origin, yeah, the origin, it's less than, we got 25, so that's not, so that was fine. Number 3, I think this should be fine. I think you guys are fine with this one, easy, yeah, nothing to talk about much. Yeah, this one I showed you how to do it using short division and long division, and later on in the other question I also did like comparing coefficients. So there are mainly 3 methods that you can work on to get the quadratic factor here. Yeah, so this is also fine, I guess. So to show that the other root, the other factor doesn't contain any roots, you just need to use the discriminant. Number 5, yeah, need to know the definition of the integral there. This is a Riemann definition of integral where the strip has infinitely small widths, right? Yeah, this one I mentioned at the start of the overview there, that you would, yeah, for part C here, the limitation of t. So limitation is basically, it's just t cannot be greater than 16.4. I already said that. So I imply the answer there that if t was greater than this value, then, yeah, I said here beyond that value would have made the h negative, which is not realistic. So that is the limitation there, 16.4. All right. And that's it. And we proved it by equating h equals 0 to find that. Yeah. Okay, so that's fine. This one, yeah, I would like you to look at this one again if you don't understand fully, because it's a quartic function, doesn't quite come out often. So if you don't get any part, just go back, like particularly the part where I came up with the quartic equation there. And for any polynomial function, you can never assume always that a would be 1. It doesn't have to be 1, right? So that's the important point there, I think you should know. And the tricky part might know first that the plus k would be the vertical transformation, like vertical translation. You're shifting up or down. Yeah, because we know that it needs to move up by some amount. So we know that it should be in that range. Yeah, and 2, 4, 3 here is by calculating where this point is, and we need to move it up by that point to make it no longer intersect at 4 points, right? So that's the limitation of k, 0 to 243. All right. Number 8. Yeah, this is proof. So just find it through there. Should be fine. We just spot the error there and just write the correction. And again, the complete proof would require that you go through for all cases of m, because you can have multiple of 5 and then multiple of it plus 1 or 2 or 3 or 4. That's it, 5 cases. So if let's say the question will go too harsh, then you might have multiple of 6. Okay, so you would have multiple of 6 plus 1, multiple of 6 plus 0, or like 6k, and then plus 1, 2, 3, 4, 5, 6 cases, right? And so on. Yeah, so this is fine. So you just keep on doing it and be careful with the algebra there. Should be fine, no worries. Yeah, this one is probably trickier, modeling here using exponential. Well, basically the proof part is when you need to maybe try get some cue from, like, because you see that the final form has an ln here. That's why when I was at DIT, I had to think about how I would go from what I had here to there, right? So I didn't know what to do. So basically, because there was an ln, that's why I have to make this thing the subject, so that I can do the ln there, like the reverse operation, moving to the other side, and then things just worked out fine. Yeah. So sometimes the proof question, you don't need to know what to do. You just figure out what you can do. Yeah. You just need to figure out what you can do. Think about the choices that you can, like the options, the routes that you can take, and just pick the best one at a time. And it should lead to the right answer. I mean, provided that the options are mathematically correct, yeah, and relevant to the question, yeah. In this case, we just try to rearrange, right? So I just went for that and got the answer. So that's fine. An iteration formula here, fine, okay. Question 10, vector, easy. Well, I almost made a mistake there. I did earlier and I corrected it. So these are the sides, and then we proved that it is an isosceles as well as a right angle triangle. So isosceles proven by just showing that there are just 2 equal sides. If there were 3 equal sides, would have been called equilateral triangle, right? And right angled, yep, so just use Pythagoras there, yeah, would be the best choice. Number 11, yeah, this is also another modeling question, and again, this is another exponential. So the tricky part is part B. You just so the tip here is you don't need to substitute the k and the a in early, because it might get you confused actually, because they have here minus k. They don't do anything to k, so we don't need to substitute k to anything, right? Don't rush in substitution. You don't need to, right? The limitation to the model, yeah, yeah, I checked that, and the value of the car can never be smaller, which is not realistic. I mean, basically, if you leave the car for tens of years, it's gonna be worth nothing maybe. All right. Okay. Number 12. This one is good actually. So it makes you think a bit about how to get the last answer there, the part C. But the first part, yeah, verify. So verify doesn't equal show or determine or work out or calculate. Verify is basically just substituting the answer, knowing it is 6 here, showing that it would give you the right value of y for both, like they give you the same value of y. So that is verify. Verify is like showing that it works backwards. But if it said show that C and L intersects where x equals 6, then you would have had to solve it algebraically here, and would have had to do part B and solve it and show that it's equal to 6 and others. Yeah, and part B there is just we just algebraically derive that this is the equation where you can find the answer of intersections, and yeah, part C you just have to solve for the other x value. Yeah, exact value is this. Yeah, so it's in the third quadrant. Just have to look at the graph there, not just blindly get any other value, right? Yeah, this is integration, so that's fine. By part works here. Not sure if other methods would work as well. Substitution, that's going to give you quite some work compared to by parts. Reverse chain rule, I don't think it works here. No, it doesn't work. No. Yeah, I think by parts the best one here. By parts the best one here. Yeah. So you see, sometimes by parts work well when you have different types of function multiplying together in the integrand. Substitution, however, works well mostly when you have the same type of function like this. But in this case, I think substitution will give you a headache. You can try do that. See if it works as well as my method here, and if it does, then give me a comment. Yeah, but I'm not going to try here because I prefer doing it in by parts way. I mean, in some questions I prefer substitution, of course, depending on the case, but in this case I think by parts work better. Yeah. 14. Yeah, this one. Yeah, this one you just have to expand, right? And of course the 30 degrees there is a basic angle. So I mean, if you have the memory of what sine, cos, and tan for 30 degrees, 45 degrees, 90 degrees, 0 degrees, it would be great. I mean, you should. Yeah, just go search YouTube. There are a lot of tricks to remember the basic angle. There are finger tricks. You can use finger tricks, but if you keep working on recalling, active recalls, it's going to be in your hard disk memory, just like how it is for me. So you have to, I mean, in my country, we don't have we can't use a calculator until college. So we have to remember all those values. And yeah, since then, I never forget, yeah, those values. Anyway, yeah, so part B is just solving it. So you prove from part A and use it in part B. So that should be fine. This one, number 15, yeah, algebra. Nothing particularly complicated about the shape here. It's just simple lines, the arc, the radius, and the straight lines. Nothing particularly hard. It's just that you need to get the information and work on, like part A is the critical point here. If you can't get part A, then, well, it's fine. I mean, if you didn't get part A, then you could have used part A to maybe do B and C, yeah, and that's still fine, I think. This one, yeah, this one, it's good that they show you that you should get this, right? But I just didn't look at it. I just try search the formula sheet and look for the formula, how you integrate cosec, right? But anyway, the substitution part might give you a headache if you don't know what to do. But basically, yeah, basically just that part. You got to go through very thoroughly through the algebra, substitute it correctly, be careful with the sign and everything. And the And the point that people usually forget here is the bounds, right? Because they don't tell you they're A and B, so you just have to figure them out. The bounds must be for u, not for x, right? Because we're using substitution here. Okay, and part B, we just sub in the limits and then we get the answer. So that was it, guys. If you find all that was helpful, please like and subscribe to support me, and I'm gonna grow more of these videos in my channel, including other examinations as well, like the ones that they take in the UK, like UKMT, and others for the admission in the university. Please help support me. Help me grow this channel even more, right? The more this channel grows, the more I make videos. That's simple, right, guys? We have a deal here. You don't need to do anything else. Just subscribe. And I'll see you in the next video. Thank you. Bye.